Okay, guys. Hope everyone's doing well. Um, Normally, I get a little work done on the weekend, trying to like getting the asynchronous assignment prepared. I didn't this weekend. I was kind of overrun with other issues, so I'm going to have to get that asynchronous assignment going. I have an account on Quizzes, so hopefully I could at least today's asynchronous assignment is not going to come out until a little late. I apologize for that. I have another class I have to teach this afternoon, so it is going to come out a little on the late side. So it'll be short. It'll also be my first attempt at Quizzes, so I guess short is okay. And then following up, if that works out well, we'll continue using that as well. All right, so last time we kind of got cut off. I turned into a robot, but it was okay. I really didn't want to go into the next subject anyway. It was another kind of a big subject, and so I didn't want to hit that last time Friday anyway. So it's okay. It worked out all right. But I did want to go over again what we did talk about last time, and multiple focus, and then receive focusing. And if you're not confused by receive focusing, I'm impressed, because it is confusing to talk about. So without further ado, let's get into multiple focus. So I've drawn three focal points for myself here. It's kind of get an idea of how to draw my lines, which means, of course, on the side here, there's going to be, let's take this off for a second, there's going to be a little triangle, little hashtag there, whatever, depending on the machine you're using, we have little triangles that shows 3 focal points. There's always going to be at least one. You can't have less than one, because there's always a natural focus. But even the one focus, when you're down the one focal point on the on our transducers, these multi-element phased transducers, phased array transducers, it's probably not the natural focus that if you see the 1 caret somewhere, it's just, it doesn't take any more time or really effort by the machine to create one focus. So it's always going to have the 1. Now, multiple focus takes up, I was going to look that up. I was going to ask my daughter to figure it out mathematically for me to make sure I'm not saying it wrong. But basically, every time you put a new focus in, you're doubling the amount of time it takes to create an image. Because every focus, 176, yeah, page 176. Every time we focus, we add a focus, we have to add a beam line to create that extra, to create that focus. So adding a beam line takes time. You have to send out that beam and then wait for it to come back. So let's see, I'm going to focus, put a little dot right there to give me, I need my little cheater here, and I'm going to use a more cheating. So more or less, here's my first focus for this 3 focus beam. So when we say a beam, kind of in a way, what we're really saying is, in this case, 3 beams. 3 separate pulses make 1 beam. And really, we're not even really beaming anything, are we? Oops. There, I suppose. Get my little cheater here. There's my second pulse. The green was my first pulse. The blue is my second, and the purple here will be my last. Okay. So remember, when we talk about a beam of ultrasound or a beam of sound, it's not a continuous beam. We know this. We know that we use pulsed echoes. So this beam, as it were, is really pulse, pulse, pulse. And then it's going to move over and do another pulse, pulse, pulse. Well, the move over part we'll have to talk about today. What this has essentially created, and let's use red. Essentially, these three separate pulses have created, we use a large beam here. Okay. So I'm going to pull that away for a second. Pulse, pulse, pulse. Each one of them, each pulse has its own characteristic. It's focused at a different point. It spreads out differently at the focus. But what it essentially creates is a beam with a long focal zone. And we think of it, because this is happening so fast, we think of this as a single beam with a long focal zone. Well, it's really not. It's three separate ones kind of piled up on top of each other. And if you think about it, what the machine will do is at 13, at 13 microseconds, and let's say it's the first focus is at 1 centimeter. It's paying attention on this one. It's kind of paying attention to the green, although I've drawn over it pretty much. That first focus, it's paying attention to the focal zone of that first one. So at 13 microseconds, it's paying closer attention. The machine's kind of paying attention there. And then let's see, at 26 microseconds or 2 centimeters, the machine, there'll be an overlap here, so we'll kind of draw it like that. And then at 39 microseconds or 3 centimeters, so the machine's actually able to pay special attention to the beam at different times. So it says, okay, I'm going to put together a single beam out of these three pulses. In the first pulse, I'm going to pay attention to the focal zone that kind of surrounds, well, basically maybe from the face of the transducer. But anyways, that focal zone that is around the first focal point. And then the next beam, the next sound pulse goes out, and it's paying attention more or less to the second focal zone. And then the third pulse goes out, and that pays attention to the last focal zone, the purple focal zone in this case. And so it's able to put all that information together, three separate pulses, but it says, you know what? I'm going to treat you has one pulse. So that's focal, that's three foci. One foci doesn't cost you any time in creating a new image. You add the second foci, now you've doubled the time it takes to create that image. You add the third, once again, you double, not the overall time, but you double the original time to make that. That's the part I got to ask my daughter about, but you keep adding time. And so 3 focal zones, 4 focal zones, 5 focal zones, when you're deep in the body, it's too much time. The machine is waiting for every one of those pulses to go in and come back. And that's just for one line of information. You have hundreds of lines side by side in order to create an image. And so maybe you start off with 100 lines of information with one focal point. Now, well, you still have 100 lines of information, but it's taking you twice as long. So it's now there's, instead of 100 pulses creating 100 lines, now you have 200 pulses creating 100 lines. Now you have 300 pulses creating 100 lines. And so it just keeps adding on and on. Okay, so I think let's see, I could probably just erase nope, I'm out of eraser. Okay. So then there's the dynamic receive focus. Now this part is a little harder, but we'll go ahead and do that again. I have you know what, I'm going to create a flat structure of some sort, and then I'll create another green one that's also flat but much deeper. Oh, I wanted light green, not dark. It doesn't matter what structure this actually is, but I'm using flat for a reason. Now these structures, they're going to receive an echo. So a beam's going to come down. That little pulse is going to come down. It's going to hit this structure here, and that structure is going to reflect something back. Now notice the reflection back is not Huygens wavelets acting together to create a narrow beam. That goes out the door. Now it's just simply an echo. And as that echo comes back, there's, these people who put this together, they understand pretty closely, they understand pretty well how an echo comes back. It doesn't come back, even though it was a flat surface that created the echo, it doesn't come back as a flat surface. There's a little bit of the spreading of the wave and a curvature of the wave. Now this curvature, if it were truly read as a curve, then it would show that this was not a flat structure, it was a curved structure, because this is coming back curved. Therefore, as far as the dumb machine says, well, that must mean that the structure was curved. Well, no, it's not. That's just the way echoes happen. And of course, the machine could say, okay, well, this is 13 microseconds. That must mean it's 1 centimeter deep. But it also knows that at 1 centimeter of depth, there's a certain amount of curvature, certain amount of spreading out of that echo that can be expected. And so on the way back up, the voltages that are created on the way back up, well, the machine can look at that. All those wires there, and those wires are going to receive they're going to receive the echo. I'm sorry, the wires, and therefore the each individual element is going to receive that echo at just the slightest difference in time. And so it's actually going to create a curvature in the electric voltage that is created. Remember, these are piezoelectric. You push on them, it creates electricity. You add electricity, they vibrate, they create sound. So they work in both directions. That curvature does not truly represent the shape of the echo, the shape of the echo producer. So whatever this was flat, but the echo came back a little bit curved, because that's what echoes do. That's what sound normally does outside of using Huygens wavelets. And so we'll come up to a little structure up here, a little structure, a little electronic doodad up here. Once again, I can't remember the, in any case, we'll get to that when we get to it. It takes that curved echo and says, no, I don't think so. I think that this structure had a flat surface, because it says it times it backwards. In other words, we have timing to create a focus. On the reverse echoes, the timing's kind of is going backwards, and so now it slows down. It says to the middle transducer, which, I'm sorry, I keep saying transducer. The middle elements receive the echo first. The outside elements receive it just a little bit later. Up in the electronics, we say, no, we're going to dynamically focus this. We're going to say, no, all of these echoes should have come back at the same time. So that's the way we're going to show it on our screen. All right, that was a mouthful. Let's get rid of some of this extra ugly stuff. Okay, that's good enough. Let's kind of make this a little bit less dramatic. Because I need to show the deeper one a little bit differently. So this guy, once again, just creates a slightly curved echo. Whoops, let's make that last one a little more curved. So let's just say this one's 39 microseconds, or 3 centimeters away from the transducer, so it's 3 centimeters of depth. It's going to have more spread of the echo. Engineers know this. They say, okay, we know if we're waiting, if we're waiting 13 microseconds, the average spread is so much. But if we're waiting 39 microseconds, the average spread of each echo is going to be even further. And so the timing is going to be even more dramatically changed. But by doing that, it's able to say, once again, even though we have a curved echo coming back, the machine is able to kind of focus that after the fact and say, you know what? I don't think it was curved. The echo might be curved, but I think the structure was flat. That's hard to explain. That's a hard one, but I'm gonna keep moving on. You guys have more questions on that? If you have questions right now, go ahead and ask. If you have questions later, ask later.
Yeah, I don't even know where to begin when it comes to asking the questions yet, so.
Okay. Well, maybe we could spend some time working on this. Okay. So page 178, the annular phased arrays. We don't have any in our lab. Now, our transducer elements, if you could look straight at it, as in like you hold the transducer, you peel off the matching layer, and once you peel off that matching layer, we should be able to see element, 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 element. And what they'll create, let's see if I can, maybe I'll just do this again. And again, maybe I could just use my other picture over there, I guess, but, and just one more. Okay, so we're looking straight at the transducer, like aiming it right towards our face. We peel off the matching layer, and this is what we see. Element, 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 element. The beam created from this, whether it's a single element transducer that's square or multiple elements like this, the beam profile, once again, if you're looking straight at the beam, it's just impossible to do, but just imagine the beam profile, let's just use a different color, would actually be more or less square. We don't really think of it. We think, I describe this as a laser beam. I draw pretty pictures that do this and all that, but there's a depth to that we're not really paying attention to yet. Or imagine this as a flashlight, and rather than having a round head, the flashlight has a rectangular head and not a lot of spread on the beam at all. So it's really well focused. If you had a rectangular flashlight, it would show a rectangular light on the wall. Now I'm talking about a really well-made flashlight, not one that spreads out all over the place. That makes sense though, right? If the source is rectangular, what you see on the wall will be rectangular as well. Or if you took a flashlight and if you took a piece of cardboard, cut a square out or a rectangle out of that cardboard, you shone the light through, it would create a square on the wall beyond that. That's actually the shape, more or less, of our ultrasound beams. We're going to get into them more in the near future as to the three-dimensional shape of our regular ultrasound beams. But for right now, we haven't really even spoken about that. So the first time we are going to talk about this is on an annular phased array. Now, these guys are different. I don't think I've ever actually used one. But they're round. Now, we've already spoken about round transducers before. We've spoken about just simply, yike. Single element transducer. We spoke about that a few chapters ago because, like in chapter 10, because a single element is the most basic form of that a transducer could be created. Not very useful, but it's the most basic, and so we don't really use them. That single element, let's get that back up there. This guy actually creates a round light on the wall, let's say. If this were a flashlight, a well-made flashlight, and you shone this on the wall, you would see a round light on the wall. That's what annular phased arrays do. But they do have multiple elements, which means with multiple elements, and by the way, the name is phased, which is phasing is timing. With these, you're actually able to create multiple focal points, or you're able to change the focal point. In any case, both are true. Multiple focal points, changing your focal depth and all that, both of those are true. So this image is looking straight down. You know, you've turned the flashlight right at it, and you're looking at the bulb, right? This is looking straight at the transducer. You've pulled off the matching layer, and then now instead of square or rectangular elements, you see, let's see, 1, 2, 3, 4 elements. Each one separated a little bit, each one in its own individual channel. So each one of these has a single wire to it, but only 4. There's only 4 channels and there are 4 elements. Now, let me draw this more like a I want to give the sense that this is a round structure and we're looking at it. Here, we'll do a slight. Oh, I'm pretty proud of myself for that one. Okay, so now we have, now this transducer is facing down like we've been drawing before. And it draws, it creates a, let's see, I'm going to need my little cheater here. So as before, it's going to have a focal point. It's going to have a beam that is a little bit hourglass shaped, just like before, and it can have multiple focal points. So I could draw second one, and then third one. Each one of those is a separate pulse. Each one of those was timed, phased. Remember, phased equals timed. These beams, the timing between elements was changed for 3 pulses, creating 1. Let's see, where's the second one? 2, 3, I can't really, yeah, I had a hard time seeing which one's which here, but basically 3 focal points or 3 focal zones. The big difference here on this is that if we were shining this against the wall, we would see a circle. If we were shining our other transducer against the wall, and you can't literally do this, you can't even slightly do this because we're talking about very small beams. If we're shining this guy's beam against the wall, it'd be a little more square, a little bit more. It's not. Okay, so it creates a round transducer, a round beam profile. The width and the depth of the beam are identical. It's a circle. The width and depth of this beam are not identical. The beam created by that multi-element transducer, linear transducer, they're not the same. Width as in from side to side, and depth as in from front to back, not the same. Okay, beating a dead horse. So once again, our focal point in where it is all about timing of the elements. If you have, let's see, a greater time difference between the outside element to the, here, let me zoom in a little bit. Between this element to this element, if the time is greater to this element to the middle element, you're going to focus it more. You're going to focus it closer to the transducer itself. If the timing between this outside element to the inside element is not as great, then your focus is pushed farther away. Now here's the thing. We learned on a linear transducer, or what we have before, the phased. I got to be careful because some of these are good. It's a tongue twister. Linear phased array. We learned that if you time the element from the rightmost element to the leftmost element, you steer to the left, I guess. And if you time from starting with the left and end with the right, then you steer the beam towards the right. How would you do that on this one? You stimulate this outside element, and the whole thing goes off at the same time. There is no right to left. There's no right to left phasing. There's no left to right phasing. You can't do it. You can do outside in, which is focusing. So these guys can electronically focus, but if you're going to steer them, they have to be attached to a mechanical transducer. Let's make sure I say that. Yeah. Mechanical steering. So let me read through this. Active elements of annular array are disc-like rather than a single element. The disc actually comprises of multiple ring-shaped elements with a common center, kind of like a bullseye. You can only mechanically steer it. But focusing, yep, you can focus outside in, just like, let me take the time here to, just like over here, you could start on the outside and then work your way in, and that creates a wave front that focuses to a point. That's focusing with the linear. You could do the same thing. Over here, and in essence, these guys are focused to a point, and then after the focus, they start to spread out, and then they'll spread out forever. Same thing. So electronically focused, you could do multiple transmit focal zones. And so what this does is these are really good at creating that really long focal zone. We've already talked about that. Remember, and let's get rid of some of these. Multiple focal points kind of creates that single focal zone. What these guys are actually pretty good at doing. Actually, let's do here. They can create a beam profile more so than any other transducer, is more or less shaped like that. In other words, a very long and narrow focal zone. Okay, let me recall from page 135. Yeah, intercrystal. Remaining information in the intercrystals. Okay, yeah. Let me read this because this I was alluding to this before. The intercrystal of an annular phased array transducer creates a shallow focus beam, and information only from the shallowest depth is collected. Remaining information from the intercrystal's reflected sound pulse is ignored. The next crystal, larger crystal, is fired down the same scan line, and only information from its focal zone is processed, so on and so forth. You know what? I might have said something wrong. I can't remember now. You know what? In fact, I did, because I was talking about phasing. Now, these are timed, but yeah. Each crystal, each circular crystal is fired by itself. Whereas over here on these linears, the linear phased arrays, groups of crystals are fired at the same time or almost the same time, phasing. On this one, and I kind of slipped my mind, sorry about that. Each ring kind of creates its own wavelet, its own narrow beam. So it would be outside fires to create the far zone. Then this guy, the middle one here, between the blue and green, that creates, perhaps that zone. And then this one here between the blue and the inner purple, perhaps that creates that zone. And then the purple by itself, that creates that zone. So actually it is multiple pulses, in this case, 4 pulses to create a very long and narrow focal zone. So everything else I said was correct, but I kind of misled you on exactly how these guys fire. They actually do, the rings fire independently. They don't, but anyway, they fire independently. Each one creating a round beam of sound, or a round pulse of sound, together creating a very long focal zone. And these guys they happen to be very good. And the width and the depth are equal. And so what they're saying is, I alluded to this before, is that let's just start with the inner one. The inner one fires, and it only listens, let's see, that was purple. It listens to this area and ignores everything else. The next pulse fires, and that's, let's see, between the purple, the second ring here, that's purple and blue, so I'll make this one blue. The next one fires, and there's a little overlap, so we'll do this. And that listens to here, and then ignores everything else. It ignores, it doesn't want to listen to places that it's not doing a good job. It only wants to listen in that particular pulse's focal zone. Let's see the next one between blue and green. I'll use green here. This one is going to listen to here. So this third pulse, it goes out, it ignores the focal zones for the first two, it ignores the last one, it only listens to this part because this is where it's focused. This is where it's getting its best information. And then the last one was, I think, black. So yeah, we'll just kind of add that. So the outer ring is listening only to information coming from the farthest reaches of this transducer. And it knows that because of timing, 13, 20, 26, 39, some other number, 52, I don't know, 50, but anyway. Yeah, 52, I think. Anyway, that's how those work. If you damage a crystal on one of these, let's say we damage this crystal, and we can zoom up a little bit so you can see what I was saying. Let's say we damage this crystal. That was represented in the beam by the color green. If we damage that crystal, and we'll just kind of scratch this whole section out. Because now we're not creating a pulse that focuses there, and we're not particularly listening there. What happens is the machine go away, listens to the purple, it listens to the blue, and it listens to the black, but it does not listen here. There's nothing, and there's nothing happening there. And so it ends out on your screen, if you see on page 179, we have a image, and by the way, this is the shape of this image because it is a mechanical transducer. It has this pi shape. So let's go back to our color scheme again. We see everything in the purple region. We see everything here just fine. And in the blue region, we're seeing everything just fine. And in the black region, we see everything just fine. But in the green, nothing there on our screen. Nothing there because that particular element was broken. So a damaged PZT crystal, first of all, image shape, fan, or sector. Damaged crystal, this will appear as a horizontal side-to-side band of dropout at a particular depth. Recall that each ring of an annular array is responsible for collecting image data from its focal zone. So if the innermost ring malfunctions, the most superficial, in other words, the innermost ring, if purple ring were to malfunction, then we would have nothing at the top of the screen. But that's not what happened in our case. Our third from the middle ring, that one malfunctioned. So this ring was good, this ring was good, this ring was bad, and then the final last ring was good. Let me go back to the beginning of this chapter because we have that list of shape and number of active elements. Ooh, how many? Okay, the book doesn't give us a number of elements that are typical for this transducer, but we do know the shape, that they are ring shaped. Automatic redirection of sound beams to create an image. Redirection of sound beams, that's what what he's asking about there is steering. These can only be mechanically steered. They cannot steer electronically. Focusing, that's done electronically because we can focus using different elements. Each one has its own focal point. Shape of the two-dimensional image. This is what it's going to look like on our screen. It's going to be fan or pie or sector shaped. Consequences of a damaged malfunction, a damaged or malfunctioning active element. We get dropout from on our screen. It's kind of like goes right to left, left to right. Okay. Oh, okay. Now these linear sequentials. These are fun. So we're learning a new word here, sequencing. And that's not like, you know, what you wear on a Saturday night or something. It's not that kind of sequence.
Oh, so you don't put those on your jeans and make yourself sparkle?
No, we're not going to be bedazzling anything in class, but I mean, if you can, if you want, but. All right.
I'm going to make these scrubs pop.
Careful, you know, when every time you talk, I turn into a robot. Okay, that's probably about the middle there. Okay, what am I doing? I don't need this just yet. All right. So we've already spoken about phasing. I take this entire set of elements and I start, you know, 1, 1, 2, 3, 4, 5, 2, 3, 4, 5, and keep going until I get to the middle. I will focus the beam because these guys start on the outside. And I've essentially just created now a wave front that is focused down to that point. So that's phasing and focusing. I can also phase from right to left in order to, got to my last one there, couldn't erase it, okay. I go 1, 2, 3, 4, 5, 6, 7, 8 all the way across. Then I create a wave front that goes off like in that direction. So that's also phasing. It's all simply timing of the elements to manipulate the beam. Well, so far we've talked about small footprint transducers. The small footprint transducer, like the linear phased array, every single element is used every single time. On a longer footprint or a longer face, the transducer really can't use every element every time, because then you would have a beam that was so wide that it would really, the lateral resolution would be horrible. You know, because if it's one thing if we have just a few elements in a row and we fire off in this direction and then that direction and that direction, and you still create a decent image with a pointy top. I still disagree with the pointy top. I don't know why it's like that. But anyway, who am I? But as these transducer footprints or faces or whatever you want to call them, as they get bigger, you can't continue to do that. So what we do is we sequence. So actually, let me zoom in. Yowza. So sequencing is a little bit more like this. Let's see, let's start with green. One, two, three, four, five. 1, 2, 3, 4, 5. That's a Spaceballs. Anyway, with these first 5 elements, I create a beam. Then 1, 2, 3, 4, 5. Then I use this next grouping. There's overlap. So with this next grouping, I create a beam. And a beam. And so on and so forth until we go all the way across, creating beam, 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 beam. Now, some of our transducer, how many beams? One wave, each crystal steering. Yeah, it doesn't tell me how many beams. So we have dozens of individual beams are created as it sequences across. They're still phasing. So let's go back to this the first green 1, 2, 3, 4, 5. Let's just add orange here. It could still be phased so that the outer 1, 2, 2, 3. So each beam is phased, so steered and or a focus is created by phasing, but then they're sequenced. So as we go across, we're using a separate grouping of elements. And of course, groups of elements are how we create the beam of sound in the first place. Now, number of crystals and shape, 120 to 250 rectangular shaped piezoelectric elements. So basically this is what I've drawn. I didn't draw nearly 120, but you get the idea. Each crystal is about a wavelength in width. So the width is about equal to lambda. They could be up to 10 centimeters long. Now, the original, be careful how I say it. Yeah. So as you guys probably know, some of the first applications for ultrasound were entirely OB related, right? We wanted to see what the baby generally looked like, position and everything, and make some measurements. We didn't have, well, actually, we didn't have phasing initially. We had very long, they called them the brick. We would have a transducer whose aperture, the face of that transducer, had to be really big because we couldn't steer. I'm sorry, we couldn't steer yet. They didn't have electronics to really make that happen, but we could phase actually. So but you had to have you actually had to have transducers that were bigger than a baby's head in order to see the entire head. We weren't able to steer. They didn't have curved transducers back at the beginning. So they had these giant brick of a transducer. You have to push it down fairly hard in order to make sure it had good surface contact with mom. And that they had to be huge, and they would go across in phases, but they weren't at that time, I'm sorry, sequencing, but they couldn't phase at first. They didn't have the technology yet. So beam steering. Okay, I have a little note in my book, page 180. There's a subsetting that says beam steering. Now, listen carefully when I say something here. I'm going to read along. With linear sequential arrays, a small group of crystals are fired simultaneously. That's what I showed you, to create each sound beam. The sound beams are parallel to each other and are typically directed straight ahead. For example, the simultaneous firing of the first 10 crystals creates one sound beam. The next 10 crystals is the next sound beam, and so on and so forth. The sound pulses originate from different locations along the face of the probe. That doesn't describe steering. What that described is literally just sequencing. That's just what I showed you right here. In fact, he doesn't talk at all about steering. Let me see, there's a linear sequenced array, linear, sequential. Yeah, no, but he does say electronic, okay. Oh, and I found there's another mistake in the book. We'll get to that when we get to it. So it's kind of bothersome. So just be aware that he is not describing beam steering. He is describing sequencing in that little section. Sequence. Anyway, so groups of transducers. Damn it, I keep saying that. Groups of elements firing to create their own separate beams. Okay.
Out of curiosity, sorry.
Yeah.
That way, I guess I don't make the mistake of confusing it. Why would he label it beam steering if it's actually sequencing?
I can only imagine he made a mistake.
Okay.
And because I just quickly looked ahead to, there is a couple of charts on page 187. And summary of transducers, table 12.4, linear sequential or linear sequential array. He dropped the word array. The image shape is rectangular. Yep. Steering technique, electronic. Focusing technique, electronic. And then he just fails to. He fails to talk about steering at all. But
I just didn't know if there were like similarities that made them similar and like just I guess got confusing, but
yeah, and actually I'm incorrect. He does talk about it on page 183. Asks the question in bold: can linear sequential arrays transducers steer sound beams electronically? Yes. And so they can. So if I were to create a beam out of those, that beam can be, let's see, let's steer it. That's why I'm staring at I'm thinking one way and I'm drawing the other thing. That's why I'm screwing up there. So here we have sequenced as it's our first grouping, our second group. Well, I'll show you this. But we've also phased. This was the first, second, third, fourth, fifth, sixth, seventh, and eighth. And that creates a beam front that's steered in that direction. So we steered that by phasing, and then it's essentially sequencing because we're not using the entire face. So if our next grouping, let's just overlap a little bit here, are those. That's sequence number 2 or group number 2, however you want to call it. I'm using the word sequence because that's what it is, sequencing. And then so then we'll 1, 2, 3, 4, 5, 6, 7, 8, 9, whatever. And then once again, that's going to create its own beam. There's that wavefront, and that's steered in that direction as well. So that's oops, got an H in there, phased steering, or steering caused by phasing, and then is sequence number 2, and then so on and so forth. And so in essence, you know, the next grouping, I'm not going to draw it all out. We'll be from here to here. That also is going to create a beam. And so essentially what we've created we've now steered the entire image in that direction. So we could literally grayscale steer. That's kind of what it would look like. Yep. Okay. Let me read along here. Image shape rectangular, so rhomboid if if you steer the whole image, but basically your image is like the screen. You know, it's a rectangular image. It's what you were using today. Some of you doing it, your carotids. Sound beams are emitted from small groups. Transfers a 10 centimeter footprint may produce an image. You cannot create an image wider than 10. Damage element, excuse me, if we just damage this element, we will still have an image. And basically, we might have a little bit of a shadow here, but eventually all the other elements kind of, they hide the effects of that one damaged element. Only a portion of the recall that only a small subset of transmitted elements fire for defective crystal effect. Yeah. On the book, it shows a shadow that goes all the way down. I could prove to you in lab that that's not what happens. It doesn't go all the way down because all the other wave fronts, all the other elements creating wave fronts and creating that cumulative Jesus. Anyway, constructive interference hides it. But anyway, more about linear sequential arrays while using why can't a single crystal be used? Why can't a single crystal be used? We could
Because
use
there's multiple aspects that are reflecting. So each crystal receives the reflection back in order to send it into an electrical system to create the image. But if you have one crystal, you're only getting one image, one echo coming back.
That's part of it, actually. So you're kind of talking about dynamic receive focusing. If you're only receiving with one crystal, you cannot dynamically focus. It just is what it is. It's an echo, and who knows what the shape of the echo was. That is one reason, but the other thing is, remember, let's say I just fire this crystal, and remember the wavelength is about equal to the width. In that case, sound spreads out. We no longer have Huygens wavelets working with us. Let's see, Huygens wavelet. Yeah. But you're right too. If you're only listening with one, you can't focus. You can't dynamically focus. We can form parallelogram shapes. I already showed you how that works. We could form parallelogram shapes with the entire grayscale, or we could just do it with the color box, which is, your steering. Whoops. Slope pattern phased. Okay. Couple of things. One thing is not really mentioned by the book right here, and that's fine. We could take our linear transducer and I forgot the term. We can, instead of creating a shape on the screen like this, or like that, which is simply steering, so it's a parallelogram, we can vectoring. That's what it's called on our machines, right? I think it is. I know on some machines it's called vector. We can create this image. So what's happening here is that this sequence of elements is creating a beam front that's aimed a little bit to the side. So it's steering to our left, patient's right, our left. And then, this sequence in the middle, that wave front is going straight down, so it's not steering at all. And then this last group of elements, that's creating a wave front like that, steering to our right. So that's how we vector. So vectoring is really steering to the left and the right at the same time. Different groups of elements are doing the right steering and the left steering, but that is how we vector. We steer in both directions. When we have our it would help if I was not in eraser mode. We have our grayscale image. We are not steering at all. In this case, our grayscale image is everything. We're phasing for our focal points. We're sequencing, going across using that group, and then that group, and that group, and beam, 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 like that. So phasing for focusing, sequencing to create multiple beams across. But then we can get this color box in here. But that's curved, or that's steered. I have to use a nicer color. So what happens here is the grayscale is imaged, and then And by the way, when you put Doppler on, everything slows down in the machine because now the machine's doing a lot more and it's taking more time to do. Now we have this color image. Let's just say maybe a couple of sequences here and here are creating this Doppler image. This Doppler wavefront is coming down in this direction. Once it's in the region of interest box, you gotta understand, the wave just kind of continues all the way through. I mean, you know, even outside the region of interest, the Doppler signal is still going through. But we only listen inside of the region of interest. So the grayscale is created with straight beams going straight down. The color box, and so you make a picture with grayscale. Then you make a picture of the Doppler. That Doppler, and then we get our pretty colors inside of here. Little blue, little some blues, some reds. That that beam was steered. And then once that color box is made, you go back, you make a grayscale image. Once that grayscale image is made, you go back, you make a color image. And it happens so fast that we don't see this. All we see is a color box in the middle of our screen on top of a grayscale. They're not made exactly at the same time. It's impossible. One is made, then the other is made. One is made, then the other is made. Let's see what they say. Return to grayscale anytime it was created during color. Pattern science. Slope and the sound very straight down. However, color. Yeah, and so that's what it basically says. The last paragraph on page 183. These are completely separate pictures, but it's happening so fast you don't even know it. I have a little note in my book. I just want to note to you, and I don't really know that you'll ever need to know this, but on the SPI they might. Put it this way, different authors have slightly different takes on the linear sequenced array. And I did allude to this when I was talking about the brick, the big transducers we used to use. Other people, I never used them, used to use for getting the baby head. They were sequenced. The brick was sequenced. You couldn't make a beam, you couldn't make a single beam out of a transducer that's literally 10 inches long. The lateral resolution would be unusable. So they were sequenced, beam, 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 all the way across, but they couldn't steer. So the same terminology, linear sequenced array, 20 years ago, 30 years ago, 25 years ago, how old is ultrasound? Let's say 25 years ago, kind of like the dawn of ultrasound. Linear sequenced arrays could not steer the beam. They could not do that with the color. If they even had color, I don't know. I can't remember if they did. But if they did, they wouldn't be able to steer it. So they probably didn't. They couldn't steer at all. The same terminology, linear sequenced array, is still used today, but it's a very different transducer. It's no longer the brick. It's a smaller transducer that's far more dynamic. 1130. Well, let's go back to that page. So shape and number of active elements. What do we say? What did we say about the number of active elements? 120 to 250. Automatic redirection of sound. Old ones, no. Modern ones, yes. We can steer electronically. Electronically steer. There's 120 to 250. Focusing, yeah, focusing is phased focusing. So electronic focus. Shape of the beam is generally rectangular. It could be a parallelogram, but in general, it's rectangular. Consequences of a damaged, and we already showed you, drop out underneath that one element. All right. So I'm just going to start on the next one. I don't want to finish it. It's 11:30. I've got things to do too. So, but this is so similar that we can go ahead and talk about this. Damn it. All right, just do that. The curved transducer. Looks a bit like a Cheshire cat. Once again, 120 to 250. You know, those are averages. I'm sure there's more or less in some. Rectangular shaped strips of piezoelectric material side by side in a bowed line. So that's our curved. Also called convex, curvilinear array transducers. They are array because it's a group of them. The array is large. The acoustic footprint may be as big as 10 centimeters or long as 10 centimeters. The acoustic footprint is not the aperture. Oh, I want to talk about that. Note that the active elements in a convex sequential array are similar in size to a linear and much larger than those found in a phased. Remember the phased array, the width was what, quarter to half, but once again, these are going to be about equal, right? About equal to one wavelength. The width is equal to one wavelength. Once again, it's a sequential array. So we will beam with this group, then that group, and that group. I probably could have drawn quite a few more elements, creating a beam that goes off in this direction. And then that direction. So here's the thing about curved transducers. They don't really steer. They don't steer mechanically, and they don't steer electronically. The steering, and I put that in air quotes, is done by the fact that it's a curved transducer to begin with. So the beam is directed straight out of the crystals, but since the crystals are arranged in an arc, the pulses travel in different directions as they radiate out. So steering, what do we call it? What do we call this steering? Let me see something. Convex image, electronic steering. Page 187 is wrong. I'll tell you that before we leave. I'll tell you why it's wrong. So yeah, I mean, how do you call it? Steering is done by the fact that it's a curved transducer to begin with. The shape that it creates, they call it a blunted sector. Oh, that's a horrible picture, isn't it? Now that I'm backing up on it. A blunted sector. Well, okay, so a sector created by our That's a sector, little birthday party hat. A blunted sector, well, I'll just go ahead and use this. God. All right, my drawings are getting worse and worse. I need to take a break here, but the blunted sector is, gosh, what do I call it? I call it the bundt cake of images. Has a curved top at the top of our screen. Well, because why? Because that's the surface of the transducer itself. When we're looking at the top of the screen, we're looking at the very, very top of the screen. You're looking at the transducer itself, in a sense. You're looking at the very face of the transducer. So if we have a curved top of our screen, we know we have some kind of curved transducer or convex transducer. It can focus. Let's say this green line here, we could start on the outside, 1, 1, and 2. It's not realistic. We should have a lot more elements here, but that you can create a focus point, but you can't steer, or at least they don't steer, which is a real problem when it comes to the color box on a curved transducer. You see, on this linear transducer over here, this linear sequential array transducer, or the linear as we just generally call it, we can steer that color box. Well, as you guys know from doing carotids, that's really useful. Steering really helps with the Doppler angle, because you can't always heel toe it as much as you'd like. So steering really helps us out. There's no steering of the color box. You can move the color box, and the color box is going to be shaped a little bit like that too, a bit of a rounded top. You can move the color box from side to side and up and down, but you cannot steer it. The beam lines creating that color box are still coming straight out of the transducer, even though it seems like it's curved. So and people don't really, and I don't really even think about it too often until I get to the point where I need to get a good Doppler angle while using a curved transducer. It's very difficult, because every time you move, every time you get on your heel, you still have a straight color box. And so if you can't, it's harder to do. So focusing is electronic, just like linear development's curved spike pattern for focusing. Dynamic receive focusing you can do. Image shape is blunt sector shape or bundt cake. It appears to have a bite taken out of it. Damaged piezoelectric crystal is going to be similar. So if you have this one damaged crystal here, it's going to cause a dropout underneath that crystal. So I just want to say something on page 187, table 12.4, on the line for convex. It says image shape is blunted sector. Steering technique, electronic. No, it is not electronic. That is incorrect. I don't know why that is in there when this is. Yeah, he clearly describes beam steering as not electronic. It's just simply the shape of the transducer itself. So then focusing electronic, that part is correct though. So just a little mistake on table 12.4. But I'll leave it there. Well, of course, we'll review this. Testing. I know some of you have asked about that. We'll go over last week's test on. Well, we could do it. Let's do it tomorrow. I know tomorrow is vascular for you guys, but we'll go over that. We'll go over that tomorrow. We could easily take time out of vascular. That I'm not worried about. So we'll do that. Let's see. We're on chapter 12. And what did we just test you guys on?
8 and 9.
8 and 9. 10, 11. Okay, 11's so short that it doesn't even count. 10, 11, 12. That'd be a big test. Okay, let's do 10, 11. Let's only do chapter 10, 11. That's how it's already set up anyway. And we'll do a little bit of review on Wednesday. We'll come in. I have to make arrangements, but we'll all come in on Friday to take. It just takes so much time out of class. All right. Well, we'll take a test on Friday. Whether or not it's at home or in class, I'm not sure, because it's a real pain. And then we'll kind of be caught up. Vascular 2, we're actually behind on testing for vascular. So, but we'll do that next week. We're okay. We're okay for that. I'm not worried about vascular. It's not the focus of this semester. This is the focus for the semester. So. All right, let's actually probably stop recording at some point.